This plug is about an important topic in statistics, namely hypothesis testing. A nice way to introduce hypothesis testing and the important concept of a null hypothesis is through the so-called lady tasting tea experiment. So this is an experiment devised by Ronald Fisher in the 30s, and the story goes something like this. There is this lady who claims that she can tell whether the milk or the tea was added first to a cup. To evaluate this statement, Fisher set up a null hypothesis called H0, stating that the null hypothesis is simply that the lady has no such ability to tell whether the milk or the tea has been added first to the cup. Then he designed a randomized experiment where he offered the lady 8 cups of tea. In 4 of these cups, milk was added first, and in the remaining 4, tea was added first. He then randomized the position of these cups. He then asked the lady to determine in which of these 8 cups milk was added first. It's not difficult to show that in this case, if you just randomly select 4 out of 8 cups, then your chance of getting all 4 correct is 1 out of 70, or about 1.4%. So Fisher decided to reject this null hypothesis if the lady gets all 4 cups correct. And the basis for this is then that there's only a 1.4% probability that you would get all 4 cups correct if you were just guessing. So this is the basic idea behind hypothesis testing. You have a null hypothesis, you collect some data, you check if the data is consistent with the null hypothesis, and you reject the null hypothesis if the data is inconsistent with the hypothesis in such a way that there's a fairly small probability that you would collect the data when the null hypothesis was actually true. Let's redo this example slightly. So now I pour n cups. For each cup, I randomly select if I'm going to pour in the milk first or the tea first. So in this case, there's no guarantee that half of the cups will have milk poured first. I define a random variable called x1, which I set to 1 if the person trying out the experiment gets the first cup correctly. And I define it to 0 if the first cup is incorrect. Similarly, I define x2 for the second cup, and so on all the way to the nth random variable. So in this way, I have a sequence of n random variable. My null hypothesis is the same. So the null hypothesis is no ability. So if you have no ability, well, then the probability that x1 is equal to 1 must be precisely 1/2. You'll have a 50% chance of getting the first cup correct if you just simply guess. Also, if you have no ability, then the expected value of the first random variable is, according to this formula, summation xi f of xi will be 0 times 1/2, 50% probability that you get it incorrect, plus 1 times 1/2, 50% probability that you get it right, so that's 1/2. The same will also be true for these other random variables x2 through xn. So If you have no ability, another way of saying that is under the null, which basically means assuming that the null is correct. Well, then x1, x2, all the way to xn is an IID random sample. They're independent because the probability of success of, let's say, the fifth cup is completely independent of the success of the other cups. They're identically distributed. They have precisely the same distribution, a 50-50 chance of getting each cup correct. And they have this common expected value of 1/2. So another way of writing the null hypothesis of having no ability is that this mu, the expected value, is precisely 0.5. A person with some ability to distinguish these cups will have an expected value which is greater than 0.5. So here I have done a simulation of this experiment. In this case there are 10 cups, and this is the outcome of an individual which doesn't have the ability. So this means that this particular individual got the first one right, the second one wrong, the third one wrong, and so on. And in total, he got 5 right out of 10. Nothing special, so we have no reason to reject the null hypothesis of no ability. Here's the next person, just clicking F9. So this one got 3 right. Definitely toss him out. Next one, this one got actually 6 right. So maybe this person has a little bit of an ability. Keep in mind that I am doing the experiment under the assumption that there is no ability. If you look behind these cells in B1, for example, it says if rand greater than 0.5, 1, 0. Well, that will simply generate a 1 with the 50% probability and a 0 with 50% probability. The reason for that is this rand will give me a random number between 0 and 1, equally likely. So there's exactly a 50% chance that this random number is greater than 0.5. If that happens, print a 1, otherwise print a 0. So there's exactly a 50% probability of a 1, 50% probability of a 0. So the interesting question now is the following. Where should we draw the cutoff line for rejecting the null? So if I look at the average here of individuals performing this random experiment, I see a bunch of different averages. We would like to reject the null hypothesis when this average is larger than some constant that we would like to determine. We want to make this constant large enough such that there's a fairly small chance that we will reject the null hypothesis when it's actually true. How small? Well, that's a question that theory can't answer. This probability is called the level of significance, and it's typically denoted by alpha. Common values are 5% and 1%. So that means if I decide on a level of significance of 5%, then I should pick my cutoff limit in such a way that at most 5% of the individuals trying this experiment with no ability will actually get a result which is above this cutoff limit, compelling me to reject the null and claiming that this person has an ability. That, of course, is a mistake on my part, but at least I know that there's only a 5% probability that I will make the mistake. If I want to be more certain, I pick a significance level of 1%. That will increase the cutoff level, making it even less likely that people with no ability passes the test. But it also has the disadvantage of having people with some ability not being able to pass the test either. So there is a trade-off in the selection of the level of significance.